All right, so in this video, we're going to be looking at how to find the tangent plane to a surface in a parametric surface form, and then also the normal line to the same surface. So in 3-space, parametrized surfaces have two variables because they're surfaces. And so our parametric variables are u and v typically, although, these are arbitrary. We can call them anything we want, but we're going to use u and v. And to find the normal vector to the surface that we need for the plane, we're going to have to calculate the partial derivative for u and the partial derivative for v, and then create a cross product, because both of these derivatives are going to be in the plane, in the tangent plane, and we want the vector to make the equation in rectangular coordinates. We need the vector perpendicular to the plane. So we'll do the cross product to get that normal vector. So the tangent plane to the graph, we want to find the tangent plane to the graph given in this form, and then at this point. Now, this point, this is x, y, and z coordinates, and we may have to find what values of u and v we need to obtain this point in the original function in order to evaluate our vector, see which direction it's pointing in. So just be aware, this is not like uv values. This is x, y, and z values. All right, so we're going to start by taking the partial derivatives for u and v, since that's what we need to get started. So the derivative for our u function, again, let's go back and look at it. The derivative for u is, the u comes out 2 cosine v. The derivative for u here is 3 sine v, and the derivative for u here is 2u. So that's what we have here. And then when we take the derivative for v, then the u's stay, but then cosine becomes minus sine, sine becomes cosine, and the k component becomes 0 because there's no v's in it. And so now we have our two derivatives, and so we're going to need to take our cross product. So we set up our cross product determinant. And in the I component, we're going to have 3 sine v times 0 and minus 2u times 3u cosine v. So we're going to get 6u squared cosine v. And then in this component, the j component, remember there's a minus sign out front. This is 2 cosine v times 0, and then 2u times minus 2u sine v, but we're subtracting, so that becomes a plus. And then the minus sign out front makes it minus again. And then in the k component, we're multiplying here. So this will be 6u cosine squared. And here, we're also going to get 6u sine squared. Cosine squared and sine squared is 1. And so we're going to end up with, if we factor out the 6u, just 6u in that k component. Now, to get the vector at that point, we need to find out what u and v are. Again, this is x, y, and z. So we're going to set each of our equations equal to these values and then try to evaluate where this would be the case. Now, the easiest one to solve for, it actually turns out, is going to be this one, because u squared is equal to 4, means that u is either going to be 2 or minus 2. And then we can use the other two equations to kind of pin that down. If we look at y equals 6, then if sine v is equal to 1, again, we've said u is 2. We plug that in for u, then we get 6 sine v is 6. That means sine v is 1, and then v is pi over 2. And then we can verify that our signs work by plugging in this into the final equation. Is cosine v of pi over 2 0? Yes, it is. So the u value doesn't matter. Now, we could get a second parameterized point at another value, but we only need to obtain one vector. So we don't have to obtain every possible vector for this example. Now, the normal vector then is going to be plugging in the u and the v values we obtained. U is 2 and v is pi over 2. We're going to plug those in to our normal vector in order to get that vector pointing normal to the surface. So we plug in u is 2 into, again, this is the vector we obtained from doing the cross product. This component, cosine of pi over 2, is going to give me a 0. Here, if I plug in u is 2 and v is pi over 2, this is going to give me a 1, and so I'm going to get a negative 16 because this is negative 4 times 4. And then over here, I just have 6u, so it's going to give me a 12. So this is my vector perpendicular to the surface. And then together with the point that I was given, I put that into my plane equation in rectangular form. So 0x minus 0 minus 16y minus 6 plus 12 times z minus 4. And this simplifies a little bit. Or I can, this is my plane equation. And if I want to write the equation of the line, I can't do that in symmetric form because I would divide by 0. So I can do this in parametric form, in RT form, vector form. And so my x component is 0, and then my y component is going to be that slope coefficient that from the normal vector minus 16t plus the point that I started with, so 6 minus 16t in the j component, and then the 12 plus the z coordinate, 12t plus 4 in the k component.